Hi, good afternoon. Let's start. So before we start, I realized that there's some problems in the video on YouTube of last class that your pictures kind of cover this part of the screen. So if you're watching this on YouTube and you find this annoying, you can see the handwritten tablet notes on Moodle. And I'll try to be careful not to use this part of the notepad much today. Okay, so let's continue what we started last week. So last week we talked about two of these paradoxes that are about counterfactuals, are about we made a measurement and then we start reasoning about what other measurements could have been done or what measurements could another person have done in between, and try to think about what outcomes we could have gotten, and we reached counterintuitive results in both of them. But there's a criticism that can be made here, which is that, well, counterfactuals, meaning we are thinking about something that could have been made, not something that was actually made. So maybe it's not a big deal if the results are not so intuitive. So today we'll talk about this. We'll try to address this. So the first thing we'll do was that we'll talk about counterfactuals in real life. So if you write the tutorial, the first exercise was a little bit about this. So it's about doing this kind of logical reasoning about all the possibilities, of which not all of them were done, like this this game with beer, also all these logical puzzles where people have hats of different colors or have eyes of different colors and try to guess the color of their own eyes or hats, depending on what the other people, how they are behaving. All of this is counterfactuals. But then we'll say, okay, so let's try to get rid of these hypothetical measurements and replace them with actual real measurements. And in order to do this, we need to understand better what a quantum measurement is. So we'll talk a lot about quantum measurement as a physical process, and this will be more technical. You did this already a little bit in the tutorial, so now we'll go a bit slower. And then we'll see that there's two ways to address this criticism. So either we will replace the measurements by kind of weaker measurements in which we have less interaction with the system we're measuring, we get less information, but we disturb it also a bit less. This is what we'll do next week. Or what we do this week is to replace these hypothetical measurements by actual performed measurements by different agents. And this will lead us to multi-agent paradoxes. So let's see how far we can get today. So let's just recap how hard this experiment went. And there we saw that through some means we prepared this state, right? So in the original experiment, it was an electron and a positron that could or not annihilate themselves. But what matters is that at some point we had this state, which is 1 over square root of 3, and then 0, 0, 0, 1, 1, 0, which is kind of a nice, funnily symmetric state. And then we have two agents, each of them gets 1 qubit, and each of them can perform a unitary, which could be either the identity or the Hadamard, right? And then they measure the qubit in the Z basis. So Alice here will get an outcome, A, and Bob gets an outcome B. And then we thought about all the probabilities of all the things that can happen, depending on what these measurements are, right? On what these operations are here. And we saw, well, if they're both the identity, if none of them applies the Hadamard, then we can read directly from the state that they cannot obtain the outcome 1, 1, because it just has no overlap with the state, right? So that was probability 0. Then we saw through some calculations that if they both apply the Hadamard here and here, then the probability that they both got 0 was 1 over 12, which is larger than 0. And then we thought, okay, what happens in this case? What does Alice think that Bob could have gotten? And what does Bob think that Alice could have gotten if they don't know what the other did, right? And we saw, well, in this case, Alice, if Alice is in this situation, so she got 0, she knows that she applied the Hadamard, but she doesn't know what Bob did. And she thinks, well, if Bob applied the identity, then for sure he got outcome 1. And Bob thinks the same, because the set is symmetric. If he gets 0, when he applies the Hadamard, he thinks that if Alice applied the identity, then she must have gotten 1, right? But this, if we took these two statements together, then this would mean that if both of them had applied the identity in this case, well, both of them having applied the Hadamard, they think that if the other had applied the identity, then they would have outcome 1-1, which is precisely what was forbidden to start with. And at this point, I understand it can appear a bit unclear what the contradiction really is, because we're not really applying the same. I mean, it's not the same conditioning on this side of the probability distribution that we're combining. So today we'll get into more detail over this. First, let me just talk a little bit about what counterfactuals, how we apply counterfactuals in real life, and how we take them for granted. And although we'll keep providing more examples in the tutorials, maybe let's just give some examples here. So one is in games with complete information, like chess. So when you're thinking about your next move in chess, you need to think about all the possibilities that what your opponent will do, right? So I can say, well, I move my king there, or my queen there, and it looks like a good move, but it's actually there's one very contrived option that if Bob sees it, he has mate in 5 moves. Okay, and if you see this, you just don't make this move to start with. You don't try to model, oh, what's the probability that Bob will actually see this, right? How smart is my opponent? That's kind of bad form in chess. You just don't do it. Even though at the end of the game, this is a possibility that never happened, it influenced your strategy, right? So it was a future action by an agent that never happened. But we use it much more in games of incomplete information, like in poker. You try to guess all the time. So if my opponent has an ace, then they would raise now. They didn't raise, therefore they don't have an ace. This is a very basic case, but you get into like really complicated chains of logic where you think if they have an ace and they think I have a king, then they might not raise, but they raise anyway. So da 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 da. This is also used formally in online auctions, and it's also used to solve all sorts of logical puzzles, like you saw with this beer example in the tutorial. The other case where we use counterfactuals is kind of in law, or more general in game design, when we try to design what the reward and punishments are for different actions by agents. So, for example, if you're driving drunk and you get caught, you get a very high penalty, and this is not because of what actually happened. Maybe, you know, if you got caught, you were lucky and you didn't hurt anyone. It's about how bad it could have been. Right. In the same way in the pandemic, like we maybe judge people harshly who organize, I don't know, illegal parties, not because of what actually happened. They might have gotten lucky, but of the risk that there is that something bad happens. Good. So that's just to give us an idea of how counterfactuals, we seem to take them for granted. And now we'll see a bit more concretely later on. So over the course of the next weeks, how we really cannot use them in quantum theory. Okay. So before this, we'll just tweak the measurement a little bit, tweak the experiment a little bit. So we had this, and now the only change we'll do is that what is a Hadamard followed by a Z measurement. Okay, this is just a measurement in the X basis, right? So we will replace it a little bit just because it will be easier for later for doing the analysis later. We'll replace Alice and Bob's actions. Instead of applying this unitary or not, then they just choose to measure in the X or in the Z basis directly. Okay, so we will erase here this. By the way, if you have questions at any point, please ask. So they will just make here a measurement of Alice and a measurement of Bob. And these measurements, measurement of Alice and measurement of Bob are either in the Z basis or in the X basis. Okay, where the Z is measuring if you got 0 or 1, and X, what I call an X measurement, is measuring if you got plus or minus. Okay, so that's the first tweak. Okay, and now to proceed. So what we will want to do is to change this option of doing two things with actually doing two things in series, sorry, with there being here a measurement in the Z basis of some form followed by a measurement in the X basis of some form, and the same here. Replace them with actual measurements. But in order to do this, we need to understand what a quantum measurement is. So what follows might be a revision for some of you. So some of you might have been very familiar with this from either quantum mechanics or quantum physics for non-physicists, or maybe in quantum information theory. So, but we'll just see what is the physical implementation of a measurement. And you went a little bit over this in the tutorial. I'll try to go a bit slower here. So, quantum, and what a quantum measurement is at heart is just an entangling operation between the system of interest that we want to measure and the measurement apparatus. So it's an entangling operation between S, this is our system of interest, and M, measurement device. Okay. So let's see an explicit example, or explicit example that's very general. So suppose that we start in some state, say, this is your system of interest. It could be any quantum system, continuous or discrete. And let's say we have a discrete pointer. So this could be the position of a particle that will tell us in the end, this particle hit some screen, and the position of this particle will tell us we want it to give some indication over some observable in the system that we want to measure. Okay, which let's say it starts in some state by 0. This is our measurement device M. And so suppose, so this is the initial state. And we want to measure some observable. Maybe we have not seen observables in a while. So for example, if you want to measure in the Z basis, this could be just 1 minus 1, which corresponds to the Pauli Z operation, which means what? It's a projection. It's a projection into 1 with the label, into state 0 with the label 1, and into state 1 with the label -1, right? So this thing here is just a label, and this is the state you're projecting into. In this case, so this could be a bit more general, of course, but this is the simple case. So this is the label, and we make it a real number to make the whole thing a Hermitian operator. So then what we do, one way to do this is to do the evolution by coupling the two systems with some Hamiltonian. So let's say H equals A times P. So this will act on S. And P, now here, if I take this to be a continuous system, 1D system, I can think of P as really being the momentum operator. Okay, this is, of course, much more general. You could replace it here with any other operator on this measurement device. P is nice because it's just an operator. It's like it expands. It's very fine grain, and it's over the whole basis essentially. So this is just an example I'll put here. Of course, you could also just put here some coefficient, multiply the whole thing by some coefficient, but let's not do this for now. So, and the claim here that we will prove is that the system will evolve to, is that the final state will be of the form sum over k, some coefficients k, ak, and here's some phi k whose position depends on ak and time. Okay, so the idea will be that the state of the pointer at the end is going to be a superposition of being there, there, where this is the position, and being found here or being found here or being found there will be correlated with which of the eigenstates of this observable the system is into. So what are these alpha k's? These alpha k's are just, I can expand the original state into any basis. So in particular, I can expand it into the basis of the observable. So this would give me some alpha k. Okay. So we will first derive this, and then we'll talk a little bit about the consequences of this. But is the setting clear? We want to measure an observable on a system S, which is initially in any pure state, can be generalized to mixed states. This pure state can be expanded in any basis, in particular in the basis of this observable with these coefficients. We'll bring in close to it some measurement device, which is itself a quantum system. We'll evolve it with this joint Hamiltonian, and we will see that the final state of the pointer, or of the position of this measurement device or pointer, sometimes people call it, will depend on the state, or on like the coefficients and the observable applied to this state. Okay. So that's the claim. So we go and try to derive it. Okay. So first, let's not worry about what the state on the measurement device is. Let's just see what happens when we apply the Hamiltonian. So we say, so the Hamiltonian was, as we saw, A on S tensor P on the measurement device, which gives us that the evolution after some time t is e to minus I t over h bar, A on S tensor P on M. And now if we expand this in the A basis, so this is just E minus IT over H bar. And now comes here the sum over K, AK, and ket AK. Tensor P on the other system, right? Now, this object might not be very nice to deal with, because what we want to compute is going to be then the evolved state, which is going to be U of t applied to the initial state. So phi on S tensor phi 0 M. And we might think, how am I going to apply this exponential to this? And the solution is just we take this exponential, we do a Taylor expansion, we apply it, and then we come back to the original basis. We come back to the exponential form. Yep. So I'll not do it completely, I'll just show you what we get. So if we were to expand this, so you get sum over n from 0 plus infinity, 1 over n plus m factorial, and then we get this minus IT over h to power n. And then we get this sum over k, ak. Oh, sorry, I missed something here. ak, ak, power n, and pn to power n. Yep. So let me just add this here. The ak, there you go. And you may think that this is going to be a horrible object, but because all these AKs are orthogonal, in the end, the only terms that survive are the ones that have just the AK. So what you get at the end of the day is just a sum over K, sum over N, and AK, and here come just the AK. Right? Because every time we put two of these objects together that are not with the same index, their inner product is just 0. Okay, and Pn to the n, P on M. Okay, good. So this is the object we get, and then we apply this object on this state here. And because this state, we can also expand it in terms of AK. The only things that survive are the ones with coefficient AKs, and then we put everything back in the exponential. Essentially, that's it. So what we get at the end of the day is going to be our initial state. So let's see what it was. So it was some alpha K, AK. And then we get this E2 minus IT over H bar AK, and there will be N. Okay. This is the only thing that survives when we apply this, and the reason is because we expand this state in terms of eigenstates of this observable, right? So the only thing, it's just this weight has shifted to the second part of the state, essentially. So now we need to deal with this object here. So let's call this object here phi k on the measurement device, and now let's just see what it is. But before this, we have to see what phi 0 is. Well, let me just copy that before. Sorry. So this is what we're looking for. Okay. But so what is this phi 0? Well, this is a system in a continuous state, which means it can be expressed in terms of a wave function. And it can be expressed in any basis. So it can be expressed in the position basis. Or it can be expressed in the momentum basis. Let's put this bar here to just tell that it's a different function. Okay. All these integrals go from minus infinity to plus infinity. What is the relation between the two bases? So first of all, what is the momentum wave function? Sorry, the position wave function of x. This is just the inner product between the state and the bra x. And the momentum wave function is just P is just again this inner product. Okay. And what matters is what's the relation between the two of them. And as you know, this is the Fourier transform, so the inner product between the two is given by, I believe, up to a sign. Something like this. And this is how we can transform between the two of them, which I'm telling you now because it will be useful in a bit. And why is that? Well, because we want to compute this thing here. And this is very nicely expressed here with the operator P. So maybe it's easier for us to take this phi 0 and expand it in the P basis instead of expanding it in the X basis, because it would be just easier to apply this, this operator there. So we do this. If I paste again, there we go. So what is this? Minus IT over H bar, AKPM, applied on this state, dp, the momentum wave function, which could still be anything. We don't know what it is yet. This is up to the experimenter to set some initial state. So, and now we have this is state M, P, M. Okay. So the question now is, how does this operator here act on that state there? So what is P? P in the momentum basis just acts as, it just spits out P as an eigenvalue because it is its eigenbasis, right? So we use this. And again, we have the same thing of like, oh, we have an exponential here, it's very complicated, but if you expand the exponential into the Taylor series, apply it, and then bring it back to an exponential, you get exactly what you'd expect. So you get just integral dp, 0 of p, now e minus it bar, okay, and now here's the little p, which is the same as in the ket. Okay. So now this whole thing, this is just a number, right? So this is a complex number, which means that this here is just a new wave function, a new momentum wave function, right? So now we have that we can expand this state in terms of an integral over the basis with some coefficient. And this coefficient is just the new momentum wave function. So this is called the, say, psi k momentum of P. Okay. So now we can transform it back to the position basis to see what's happening to the state. So we just applied inverse Fourier transform. Essentially, we go back and we just need to apply this here. And this gives us what? Well, so let's write here in the position basis. So this is momentum. And the position basis, we go to k of x. So it's x to k of in m. So this is going to be just a number. Let's move it to the next page, maybe. Well, no, let's put it here. So this is going to be x applied to this whole thing here. So dp, this new number that we found, p. And now the X can move inside there. So you're just gonna get dp p, and this inner product, which we saw was this exponential. So let's move it. So now we have that the position wave function is going to be over dp. And what was this inner product that we saw? It was e to I x p over h bar with a factor of square root of 2 pi h bar. And now we just replace this with what we had. So this is 1 over square root of 2 pi h bar dp. And what was that? This was the original wave function. Oh, this should be a p here. Sorry. Yeah, that's correct. This was the original momentum wave function, and now multiplied by this factor that we saw, which was minus it over h bar akp. E I x p over h bar. And now there's many factors here that are the same, so we can group them. So I is the same, h and p. Yep. So we group them. 2 pi h bar dp. The original function. Now we have e I p h bar. And now what we have x from the right. We have x from here minus this thing from the left. Minus t ak. Right. But then this whole thing, this whole thing, because this integral goes from minus infinity to plus infinity, this is just the Fourier transform of the original wave function, but shifted. You can call this thing here, let's call this x prime. So this is the original wave function just shifted by this amount here, tak. So this is phi 0 of x minus tak. Good. So okay, so where does this leave us? So what is the total state now? Total evolved state of the pointer and the thing. This was a sum over all the outcomes of the observable, the coefficients that the original state has for that observable state, eigenstate, there it was, and then came this state in the pointer. And now we know that this is k, ak of s, and now comes, let's put tensor here, the x, the original wave function, but shifted by this amount, akt, and here comes x. Okay, good. So let's try to draw this. So first of all, what's the reduced state of just a measurement device? Here in this case, in this simple example, we assume that all these AKs are orthogonal in our observable. Could be, for example, a basis measurement. Therefore, the reduced state on the measurement device is going to be, sorry, sum over k of this psi k, right? On n. Okay, so what does this look like? So let's see what it looks like at different times, because as you see, it depends here on it depends on several things. So it depends on time, it depends on how large these coefficients are, but that's not so important. And it depends also on what the original state was. So let's look at an example. Example, let's suppose that.
What's psi k again?
Yeah. What is psi k? Psi k is the state. Sorry.
But then the reduced state should include the alpha case as well, right?
Oh, sorry. Yes, of course. Yes, of course. Yeah. Sorry. Of course. Yeah.
And probably squared.
Yeah, and probably squared. Yes. So let me move this away to make more room. Yes, of course.
All right.
So for example, if the initial state was an eigenstate of the observable, so one of these would be 1 and the others would be 0, then this would be just a single pure state. If not, then you'll have some kind of mixture, which is what we see now. Okay. So let's see the example where the original phi 0 is a Gaussian. Okay, this is kind of a well-behaved set. So we can plot it like this. Let's say I want to plot here the absolute value of the wave function of the total wave function of my measurement device, and that's x. Okay, so let's suppose that's a Gaussian around 0, and let's suppose that AK has 3 eigenvalues. Okay. So at time equals 0, we have only one peak, so we have nothing happened yet. So if we traced out the system and look just as a measurement device, then we have this. Okay, and if now we measure the position of the measurement device, that's what this height here is, the probability of finding it, or this area would be the probability of finding it inside this spatial area, right? So this should be very likely, for example. Good, so now we look at time equals a bit later. One is kind of arbitrary. And then we start see this peak separating. So then we have one here for, say, this should be for the AK equals 0 eigenvalue. And then maybe you get a slightly larger peak kind of over here for AK. So suppose this has 3 eigenvalues, let's say -1, 0, and 1. And we get yet another peak, say around here, right? Where the size of this peak, so the area behind under each peak, corresponds to this coefficients in the original state. So this would be the AK equals -1, which means what? Well, if I measure the position of the particle of my measurement device now, and I find it here, then I know with pretty high probability that this corresponds to this eigenvalue. But if I find it here, for example, I can't really tell, right? But now if I wait much longer, t equals 20, then these peaks will kind of spread out. Well, no, sorry, they will just really separate. So find one here, maybe one over here, and maybe one still here, okay, one in the middle, right? So which means that now if I measure my particle and I find it here, I know it corresponds to this eigenvalue on the right. If I find it here, I know for sure it corresponds there. Now, what we'll see next class and in the next tutorial is that a weak measurement corresponds to, instead of starting with a kind of very pit Gaussian, we start with something that's much shallower, so that we're always in kind of this position that, even if we wait a reasonable amount of time, there'll always be a big overlap between all the peaks, which means that when we measure this measurement device itself, we don't get that much information into the state of the, you don't get that much information into the measurement outcome. So this we will explore next time. But now, in today's class, we want to go more into the other option, which is when we are in a situation more like this. So it's a harsher, it's a strong measurement. And we want to see what happens to people's memories and how we can model this from the point of view of both the observer that makes the measurement and someone who's looking at it from the outside. So first, I'll just draw here a little cartoon to ask, what about the observer's experience? Because now I kind of branch it out to, well, and now we come and we measure the position here. But what does it mean to measure the position of the measurement device? So we started with some, say we measured some spin. We just couple this. So what we did was to couple it to the position of some larger particle, and now we measure this larger particle. But what does this mean? Well, it means that there will be some photons that can come and either hit the particle or not, or kind of be emitted from the screen in different positions or not. And this is, again, still a coherent process overall. And then eventually some photons will hit our eyes. Okay. And this is, again, still a coherent process. And eventually this will also become correlated with our brains. So how did I draw the brain? Something like this. So that overall we'll have some state that will look a bit like sum over k, our alpha k's. This was the state of the system. Then this was the state of the measurement device. Sorry. And then there'll be some state, I don't know, eta k, of the photons that hit it, and so on and so on, and some state of my eyes that could have been hit by a photon or not, and so on and so on, and then the state, the final state of the brain. And this can be described as a big quantum circuit that is all coherent, right? But of course, we don't have this subjective experience of I'm now in the superposition of having seen the photon and not having seen the photon. We just have a subjective experience of seeing one of the outcomes. Every time we toss a coin, we toss a coin, we don't see the quantum superposition that is there at the very end, because everything is a quantum system. Caveat, this assumes that we take quantum theory seriously, at least until the human scale. Okay, so at the end of the day, with this kind of thing, if we look just at the brain, our subjective experience is kind of tracing out everything else. And that should be, again, this mixed state. Which means that we see, I mean, we are only we only have access to one of these states. For good or for better, this is the way biology works. This is the way our memories work. So after the break, we will talk about how to apply this to Hardy's experiment. So I'll stop here, and we'll see you in 15 minutes, so at 4:45. And if you have any questions, ask away. I'm just around.
Yeah, could you run over the assumptions you made about this measurement derivation?
Yeah, yes. And also, let me just make sure that this is charging. We are live on YouTube, and I did not see your chat until now. So someone said that one of Bri is missing in the exponential. So I think I fixed this already. Let me just power that. For some reason, it's not charging. It's very worrying. Okay, I'll find a solution later. So the assumption that we saw for the measurement device. Okay. So it was just that it started in a pure state, and that our object, our initial system was also in a pure state. And that's how our evolution was made by this kind of some kind of interaction between the two.
What kind of Hilbert spaces?
So in this case, so you can do again, none of this assumptions is sacred or fundamental. You can do the same with mixed states or not. In this case, it was that this was a continuous system. But if not, you can replace this with a discrete operator, and you also get a similar result. You just don't get the Gaussians. You get some projections into discrete states. We'll see this later. This Hamiltonian, of course, you can add some noise, and a very nice example is just the Stern-Gerlach experiment. So you have a spin that is in some superposition of going up and down, and what you do when you make it go through a magnet is that the spin degree of freedom, which would be here. So here they have like a Z in the spin, gets entangled with the. So in this case, it's not even P, it's the position. So it gets entangled with the operator here is like an X, and it gets entangled with the momentum part of the position degree of freedom, which makes it go up or down after the magnet, which makes the particle hit up or down. So this was the assumptions made for this part. It's not too controversial to derive this. Then to derive this, what I needed was that these eigenstates were orthogonal, which again, if you have a more advanced measurement, if you have a general POVM, this might not be the case, but you can still compute this thing. And for these graphs, what I assumed is that it was a Gaussian, right? That the initial state of my pointer is a Gaussian. You can play with different initial states and you'll get different things. And what I assumed in this part is that, quantum theory applies at all these scales. Okay. Of course, in reality, there'll be here a big, I don't know, phi k of the environment, which maybe even gets entangled in funny ways with everything else, and it can mess up this kind of neat thing at the end.
All right, cool.
Yep. Okay, good. I will stop video and I'll go look for a charger that works, and I'll be right back. Okay, let's continue. So I mentioned briefly that Stern-Gerlach experiment was an example. So let me just recap how this applies. So there you have a spin. So for example, a spin 1/2 particle that's in some superposition of state 0 or 1. This is spin up and down. And then in the what serves, so this is kind of works as the system we want to measure, and what serves as the measurement device, it is the position degrees of freedom of the particle. So it starts in the position degrees of freedom like a Gaussian that is moving to the right. So you have something like this, which means that you can split the Gaussian into the X component and the Y component. So in the Y component, nothing happens. There's no momentum and the position is 0. The average position is 0. Whereas in the X component, there's some momentum to the right. So the X position is moving. And then when you get to the middle, you have this interaction Hamiltonian that acts on the spin. And what he does essentially is to couple the spin to the Y degree of freedom. And we saw that before, that if there was here, if this was a Py, then what would you do? It would be to shift the wave function in the momentum basis to the left or to the right. So you'd end up with a particle there or a particle here after some time. But because conversely, if here you have the position operator, what it does is to shift the momentum. So you end up, we can do the calculation. I can put this as an exercise. It's nice. We end up with a superposition of the particle still being here but wanting to go up, and the particle still being there but wanting to go down. Which is why then you appear these two blobs, and the size of these blobs give you this the absolute value of these coefficients, alpha and beta. And so that's roughly the idea. But now let's see how we apply this knowledge of, now we know a little bit better what an ideal quantum measurement is. Of course, one can make many modifications now, can make them more realistic, but this is the ideal quantum measurement. So how do we apply this to Hardest experiment, which was our starting point? And we have two options, like I say. So the idea is going to be, in general, to modify from having this situation where Alice has a state, has a qubit, Bob has a qubit, they are related, and Alice applies X or Z, Bob applies X or Z. We want this to go to some form of the two measurements are somehow applied. So that nobody can tell us that we're talking about measurements that did not actually happen. So we apply some kind of Z first, and then we measure the X. So there's two ways. One of them we'll see next time is to do these weak measurements. So that this Z star is going to be something of this form that we saw before, where you just get some, you get a little bit of information, not a lot, but you also don't disturb the state much. I had this analogy last week that making a quantum measurement is like asking if the baby's asleep, and in order to find out if the baby's asleep, you open the door, walk inside, make some noise, and see that it's indeed asleep, right? So this disturbs the system, but you get some answer that is definitive if you then measure again. The weak measurement is more like going through the door, not opening, and just listening for some noise, you know? You don't hear any noise, maybe it's awake, maybe not, maybe it's more likely that it's asleep, but you also don't disturb as much your delicate system. So this will be the weak measurements. We'll go over them next week. And today, it's going to be different observers. Measure first and second, or let's say measure Z and X. Okay, so we'll see what this means. But this will be of the sort of making strict measurements, but by different people. So let's see what we mean by this. First, we're going to take this apparatus that we developed for what a measurement is, and we're going to simplify it to the simplest scenario again. So just like we did with hardest paradox, we start with this big experiment with electrons and positrons and photons, and we narrowed it down to the circuit representation. So now we're going to take the simplest case of a measurement device. So simplest case, so we want to say a measurement that only has two possible outcomes, so it's a binary measurement on a qubit, which is the simplest system we can think of. But this means that at the end, the measurement device, we can kind of gobble up all the steps here. Okay, instead of having to represent all the systems in between, we just really need a system to be correlated with the measurement device. And because we only care about a qubit, the system only has to have dimension 2. So our memory / memory measurement device, everything of this is going to be, it's condensed into being just a qubit. Okay. So let's draw it as a circuit. So we start with this state phi on the measurement we want on the system we want to measure. So some arbitrary state. Yep. And we start with our memory in some state 0. And we want to end up with this correlated state that we saw before, right? With this alpha 0, 0 plus beta 1, 1, right? Where this thing here is our psi of k, the state of the pointer depending on the device. In the simplest case, it's going to be something like this. Right? So what's the operator that does this? Well, that's just a C0 between the two. So the C0 is kind of the simplest, it's the simplest implementation of a quantum measurement. Where here, this is the system we want to measure, and this is our memory. Of course, now we have the problem that unlike in the Stern-Gerlach experiment, where you could then like really observe these things macroscopically, in this case, the memory is not a macroscopic system. It's still a qubit, which can be quite small, but you can think of this as just encoding something that could be much larger. So it's really just a simplification. So that's the Z measurement. If you wanted to do an X measurement, what would you do? Well, like we said, we just apply the Hadamard before. So we start with psi. We just apply a Hadamard before, and then we apply again the C0 between the two. Yep. And instead of starting with the Gaussian, because it's just a qubit, we start on state 0 to keep things simple. Good. So for example, yeah, I don't need to go into examples. If you wanted to, then you could put here another Hadamard to go back to the original basis, but you don't have to. We just want to create these correlations. So we'll take this simple case, and we think of it as a stand-in for the more complicated case. So what does it tell us? Now suppose that Bob measures a qubit. So Bob measures a qubit S, say. So there's Bob inside his lab, and there's the qubit he wants to measure. That's Bob. And say that someone is watching him from the outside, which traditionally is a person called Wigner. Traditionally, because he first came up with this scenario. So there's Wigner and there's his friend Bob. So from Bob's perspective, from the perspective of his brain, of his memory, he only sees one of the outcomes. He's in this mixed state and whose coefficients are the probabilities of getting different outcomes, right? So Bob's view, of course, he could think that, I know that in reality, I'm in a superposition of this and that, but my subjective experience is that, well, there was S, I measured it, I got some outcome, and then I went and wrote this outcome in my memory, like my notebook or whatever, but it was a classical outcome that I wrote here on my memory. Okay. So from my perspective, what I have is this classical state, memory of Bob, SP. SP. Now, what is Wigner's view? And now we assume, now this is a very big assumption and totally unrealistic, but we're doing foundations. So in the same way that we make thought experiments about throwing people into black holes, we can make thought experiments about considering this whole thing a very isolated quantum system that does no interactions with the exterior environment. So from Wigner's perspective, what's happening here is just, well, like we saw before, there's a CNOT happening between Bob's memory and the system is measuring. Okay? So at the end of the day, the state that he thinks there is just this coherent superposition of 0, 0, and 1, 1. Okay. So these are the two views. And again, you can think that Bob is very smart and it thinks that actually I'm a quantum system myself and I'm in this superposition. But for practical purposes, if then is going to do some actions based on this, most of the time, we don't need to keep track of all the other outcomes that could have happened. So now let's just see what happens if Wigner now decides, which is very super evil machine, to measure Bob and his memory and this spin that is here. So Wigner measures Bob, and this will be in some kind of modified X basis, because remember we wanted to have Bob making a Z measurement and then someone else making an X measurement. So we're going to have the following basis where minus, what we call minus, let's put quotes here, on SB is just 0, 0 minus and SB minus 1, 1 over square root of 2, what we call plus on SB is 0, 0 plus 1, 1 over square root of 2. And if we wanted to make this a complete measurement, of course, there's 2 more states missing. So let's call this, I'll write it here. So phi 3 on SB. You can see that this is like a Bell basis. If you're familiar with it, 2. And therefore, SB is going to be 0, 1 minus. And now we have 2 qubits for states, so it's a proper measurement. But these things, in our experiment later on, this will never happen. Later on, and the reason for this is because Bob is always measuring his qubit in the Z basis, so Bob will always be perfectly correlated with the qubit. So here you'll always have 0, 0 or 1, 1. So these things will never happen. Okay. So just so you know, this is like the complete measurement, but these 2 outcomes will never happen. So in this case, where we have this setting, well, Wigner knows that the joint state of Bob and the system is this. And this, depending on this alpha and beta coefficients, this will have some overlap with that or with that. Okay, and what does Bob think? Let's not put let's have Bob for now not speculate about his own future, about the future of where his own memory is measured, because this will give us more problems that we don't need. We'll find enough problems without this. Okay, and for reasons that we'll see later, let's call this outcome okay, and let's call this outcome fail. Okay. And this will now bring us to the full modification of Hardy's paradox, of Hardy's experiment, that is due to Daniela Frauchiger and Renato Renner. So this is the Frauchiger-Renner experiment. And let me tell you what it is. So we have now two qubits, like in Hardy's paradox, and they are again in this state. Let's call this phi 0 of R and S. It's going to be again the Hardy state. Okay, for somehow they created this plus 0, 1, plus 1, 0. Okay, and we give the first qubit R to Alice and the second qubit S to Bob. So we feed this into these two people who live inside little boxes. So here's Alice. She gets R. And down here it's Bob. And he gets S. Okay. There it is. So what we do is that at time 0, this is at time 0. At time 1, Alice measures her qubit in Z basis in 0, 1 basis. And she writes the outcome in her memory. So she has a memory A. Okay, so she has a memory R and A, S and B. We'll see later how we model this. At time 2, Bob will measure his qubit in the same basis. So this will correspond to the Z measurements of the Hardy experiment. And now come our friends. So the observers from the outside have hats, just because. So this is Ursula, and this is Wigner. Yep. So at time equals 3, Ursula measures the whole of Alice's lab, so measures R and A. In this okay fail basis that we saw before, which is the modified X basis. And at time equals 4, Wigner will measure Bob's lab. So he measures S and B in the same basis. As we saw, there's other outcomes, but they never happen. And then they'll start to reason about what happened, but let's just write here first what a circuit view is from the outside's perspective. So we start with this state psi 0, right, on R and S. And we sent it to two parts. One went up to Alice and one went down to Bob. Then Alice had a memory that starts in some state A. Bob also had a memory that starts in some state, in state 0. Alice, B. Okay. Then at some point, at time equals 1, let me do this in a different. Alice measures, which from the outside, from Ursula's perspective, is just a C0. So this is what happens at time equals 1. At time equals 2, Bob measures his qubit from the outside's perspective, it's just a C naught. He disagrees. Then at time equals 3, let's see, around here, Ursula will measure this whole thing in this X basis, in this OK fail basis. So this is time equals 3. And then Wigner will measure Bob's lab at time equals 4. Okay. And let's just name the outcomes that they get. So let's get Alice's outcome is A, Bob's outcome is B, Ursula's is U, and Wigner is little w. Okay. And now, just like in the Hardy experiment, we will post-select in one of the outcomes that they get. In this case, it will be the OK, and then we'll reason back about what other people are thinking at different times. So I hope I managed to explain at least the reasoning of that. So let's just see the evolution of the state first along this circuit here before we start reasoning. Because then the analysis is very similar to Hardy's paradox. So we had 1 over square root of 3 of 0 on R, 0 on S, plus 0 on R, 1 on S, plus 1 on R, 0 on S, 0 on Alice, 0 on Bob's memory. At t equals 1, Alice measures, which just means that she correlates her qubit with the first qubit here with R, right? So we get 1 over square root of 3 of 0 on R, and I'll just change the orders because it's a bit easier, but the index will tell you which system it is, plus 0 on R, 0 on Alice, 1 on S, plus 1 on R, 1 on Alice, 0 on S, and nothing happened to Bob yet. And then at time equals 2, Bob measures. So his system, oh, let me change color. His system will get correlated with S. And you can see that this is really just applying a C naught, 0 on A, and then we have 0 on S, now 0 on Bob, plus 0 on R, 0 on A, 1 on S, 1 on Bob, plus 1 on R, 1 on A, 0 on S, and 0 on Bob. Okay, I think I did not make any mistake here. And then the other people will, Ursula and Wigner will measure this state. Now, if I just rename these states, if I just call this the 0 of RA, and this the 0 of SB, and then I call this again the 0 of RA. You can even put a bar or something to, to remember that this is actually 2 qubits, but we're just calling it this. 1 on RA, and this was the 0 on RA on SB. We see that this is again just a Hardy state, right? We can call this, so we have 1 over square root of 3 of this 0 RA, 0 SB, plus 0 RA, 1 SB, plus 1 RA, 0 SB, right? So, and if we now think of the measurements that Ursula and Wigner perform, now they're really just X measurements in this new basis, in this bar basis. which means that now we can apply a bit of the analysis of the Hardy experiment here. So after Wigner measures, we know that the probability of getting U and W equals okay, which is the minus states here on this state. We know from the Hardy experiment that this is 1/12, which is larger than 0. So you can do this calculation yourself, and maybe we'll put this as an exercise for next week. But really, it's just a matter of projecting, using the projectors that Ursula and Wigner have, which, as you saw, these are the ones that matter. And you see that there is an overlap of twice this with this final state. So they have this overlap. So now they're going to think, okay, what happens when we go to this case? Okay, so let's see. We are at t equals 4. In the case that they both got okay. So this will correspond in the beginning of Hardy's problem to this particles going to the D detectors. And now they're going to think about each other. So let's see, let's look at Ursula's. Thinking at time t equals 3. So she just got the outcome okay. What was the state at this point? It was this. Let me get the state. So this was the state that we got, and let's just, like we did for Hardy's case, let's just regroup the terms. So we get 1/√3 of, let's group this term with that term. Okay. So here we have 0 plus 1 on RA, 0 on SP. Okay. Plus the leftover term, which is 0 RA, 1 in SP. Okay. Now this thing here was the fail of Ursula times some constant for normalization, right? So this was the state that Ursula measured. So she went and measured the first half of the state, the one that corresponds to Alice's lab. But she knows that, you know, this part had only overlap with fail. So if she got okay, it corresponds to this term, and this term has only overlap with 1 on Bob's side. So her reasoning is going to be, well, if I got okay at this point, it's an outcome, it's not a state, so I don't put brackets around it. If I got okay at this point, then Bob at time equals 2, this was time equals 3, then Bob must have gotten 1. And let's know, there's some subtlety here, so let's go back to the drawing. So again, the idea is that we are at this point here. Ursula measured, but Wigner has not measured Bob yet. Okay, so from her perspective, it's like Wigner may as well not exist, and she's just thinking about, what does my friend Bob see inside here? I don't have to think anything, but she says, well, if I got this outcome okay, this only has overlap with 1 on Bob's side. So when Bob measured this thing, he must have definitely seen this outcome 1. Yes, because our outcomes are correlated, which means that if he had seen 0, then I could only have gotten fail here. So if I got okay, I know that he saw a 1. 1. Yes, it's a 1. Yeah. Okay, so in this case, we have, let me write here, different color. We have that, sorry. Okay, with 0 is the overlap is larger than 0. So if we have this, this is the same as if you have the Bell experiment, you have a perfectly entangled pair between Alice and Bob. Alice knows that if she measures 0 in the Z basis, if Bob measures in the Z basis, he must get 0 as well, because our outcomes are correlated. So that's the kind of reasoning we have here. Okay, so now let's go back in time and let's see what Bob thinks at time. Bob's reasoning at time equals 2. In the case where he gets okay. So let's say we start with the case b equals 1. So again, we are here. Here's our state. I'll just copy it. We have the state here. So it thinks, well, you know, everything else only as 0 overlap with 1 on my side. If I got 1, then Alice must have gotten 0 on her side. So if b equals 1, then Alice must have gotten a 0. Why? Well, because that's the only state left here. And again, it's like the Bell experiment, where if I have this state 0, 1, plus 1, 0, I know that my outcome is anti-correlated with Alice's. So this is, if I had gotten 0, maybe she got 1, or maybe she got 0 from there. But if I got 1, I know that she got 0 for sure. And this is at time equals 2. So let's go back in time and see where we are, see if this is allowed. So we are here. It's a completely different system. Bob can perfectly think of Alice as an agent, not necessarily as a quantum system herself. And he knows that their outcomes are correlated. Good. So now we go back in time once more, and we see what would Alice at the very beginning, after a first measurement, think of Wigner's outcome. So then we go back in time and you see Alice's reasoning at time equals 1. And if we take again the same state, and now we just regroup it in a different way. So let's group these two together. What we get of 0 RA, and then we have 0 SP plus 1 in SP plus 1 in RA, 0 in SP. And she's like, okay, I got 0, so I'm here. Actually, at this state, it's even yeah, don't worry, no, don't worry about it. We have 0, we are here. So what is left on Bob's side is this thing here, but this is the fail of Wigner. Remember, fail was like the times some constant. Fail was the plus state, it was 0 plus 1. So what Alice is thinking is that, well, what Alice was thinking back in the day was that, well, then if A equals 0, then Wigner can only get fail in the future. Does that make sense? Because, you know, this state here has a non-zero overlap with OK and with fail, but this is definitely fail. So she's thinking this at time equals 1, that Wigner at time equals 4 will get fail. Similarly, here we were here at time equals 2, and you're thinking about what Alice would have gotten at time equals 1. So what's the whole chain of reason? So we started with at time equals 4, we know that, okay, we can start here. This was OK, and Wigner also got an OK at time equals 4. Then we saw that, well, U at time equals 3 implies B equals 1, it was. Then we saw that, well, Bob thinks that if he got, sorry, this being OK, Bob thinks that if he got a 1, then Alice must have gotten a 0 at time equals 1. And Alice thinks, well, if I got a 0 now, this means for sure that Wigner in the future will get a fail. Okay, all of these reasonings were deterministic. And now we see the problem, right? Because we started by saying that Wigner got OK. And in this case, we follow this chain of reasoning, which can be formalized in different ways. But we got the conclusion that, you know, if I'm Wigner here and I start thinking about what Ursula was thinking at time 3, that Bob was thinking at time 2, that Alice was thinking at time 1, then I would have concluded that I could only get fail, but I got the OK. So that's the contradiction. So again, what we did was to take Hardy's experiment, model the measurements as physical processes, and replace these intermediate measurements with this, just modeling, you know, the people who do them also as quantum systems and setting them outside as just a coherent operation. But still, nevertheless, we say, and this is an assumption, we say that like Ursula is allowed to think about Bob's outcome because they have nothing to do with each other, right? They're doing it at this point. Bob has not been measured yet. So why can't she not think about what Bob is seeing? In the same way that if I'm playing cards with you, I can think about your reasoning. We also said that Bob at this point can think about Alice's outcome in the past because we're at this time point here, right? And they can think, well, our systems are correlated, so if I get this outcome, she must get that outcome. And Alice at this point, this is what some people argue against, well, she can think about Wigner's outcome in the future because she knows what's going to happen to this side of the quantum system. So if she projects into the part where she sees outcome 0, there's only this thing left, and she knows that this is going to be a fail for Wigner. And some people have argued that maybe Alice should not be allowed to think about what happens after her own memory is going to be messed up with by Ursula. But, you know, that's by the same argument, I could not make predictions about what will happen after I die, right? I know that after I die and after a few million years, the sun will explode, or no, sorry, the opposite, the sun will die out. And this is a statement I'm allowed to make independently of my own demise, right? However, in quantum theory, these things seem to be much more delicate because if you follow this kind of simple assumptions, and again, there's many, many ways to formalize these assumptions. This is work in progress. Then we get this kind of very striking contradiction where Wigner sees something, and it can also deterministically predict that it should not be allowed to see this. Okay, so this is one of the variations of Hardy's experiments, which I expect you'll have questions about, maybe over the next few weeks, where you can kind of modify the same ingredients, but by modifying them again, then you get a different type of paradox. So you don't get something about counterfactuals, measurements that could have happened but did not, but instead you get a statement about a measurement that happened in the past, even if later this measurement was sort of unmade. Okay, so that's what I wanted to give you for today. And then in the next lecture, we'll see the other modification of Hardy's paradox, of Hardy's experiment, and that's with the weak measurements. And maybe the takeaway, okay, first of all, there's no resolution or satisfying resolution to this, where you keep the laws of quantum mechanics, you don't assume some collapse theory or something, and you have some logical system that people are happy with. This is active research, including in our group, including mine and Nuria's, for example. The second is that there's so many ways to formalize this that even if you have an issue with one of the assumptions, we can just tweak the experiment a little bit to just have essentially the same result, or essentially still a contradiction, but with slightly different assumptions. Yes, and so some of the active work that's going on now is trying to find a good logical system that is still resistant under quantum experiments like this. Another line of work is to try to find out what are the, how far does this madness spread? At what point should we suppose that we're Alice? At what point should we be worried that if a small part of my memory will be measured in the future, then I need to keep track of that I am actually in a superposition of seeing different outcomes instead of being able to just assume that the outcome I see is the one I need to care about. So there's a lot going on here. I will stop now. There's time for questions if you have. But we will continue to explore these kind of themes in the next few lectures. Thanks for watching so far.
Will there be notes on this topic?
Yes, there will be notes on this topic. I don't know when they'll be out. You can see the paper by Nuri and I think it's the one that explains this the most pedagogically. If you want to see now, so it's called Inadequacy of Model Logic in Quantum Settings. And the authors are Nuria and myself. So yes, it explains this experiment and the logic and the logical analysis of it. By the way, I did modify it a little bit from the original. So again, like we modified Hardy's experiment, what matters is that Alice and Bob have this state. In the original experiment, Alice measures a qubit, and then depending on the outcome, prepares something and sends to Bob. But what happens is, what matters that at the end of the day, they are essentially in this state. So it will be a little bit different than what we saw here. But yes, the lecture notes for this part will essentially be adapting that paper and adding Hardy's experiment. Are there more questions? Okay, if there's no more questions, then I'll end here. And see you all next week. Possibly I'll upload the missing lecture before that, maybe not. If I do, I'll let you know. But
Thank you.
Yep.